For those who don't know as much Japanese or maybe can't understand what I'm saying, I grew up in Boston. I spent my whole life at MIT, except I've also studied at Tohoku Daigaku in Sendai in Japan. And one of my most important experiences of my life was finishing growing up in Japan on an exchange program where I turned 20, and as you know, that's the legal drinking age in Japan, so there was much growing up to be had there. I had my first research experience in Japan, first time living on my own, and when I returned to the US, I still have some Japanese accent for the material science specialty words that I learned while at Tohoku Daigaku. And this is the same sort of inspiration I'd like to give you at Tokyo Tech, to come to MIT and learn to do research and nuclear in a different setting with us. We're quite welcome to have you. And this is something that I'll talk about during my lecture, is the possibilities to visit us on a research or an academic exchange. Because in my opinion, everyone needs to try everything they can to prevent climate change. And that means working together. And the best way to do that is to physically come over here. So you may be happy to know that in the next 2 weeks, Boston and Massachusetts will be dropping all remaining COVID restrictions. We'll have nothing left, and the door is open to come visit us. So I would encourage everyone to consider coming to MIT for some of your studies. And so what I'd like to talk to you about today, I won't talk for a whole hour, because I'm interested also in hearing your questions about the way that we do nuclear education at MIT. そして何か分かりにくい場合は、どうぞ日本語でも英語でも質問出してください。一生懸命日本語で答えるようにしますけど、if it's too hard for me, I may have to answer in English. So please forgive me for that. But I wanted to give you a highlight on how we do nuclear education differently for the 21st century, and why we need a revolution in talent, in new people, to make nuclear energy work and to fight off climate change. So to frame this talk, it's important that I'm talking to you today because the world center of nuclear is shifting to Asia. In the US, we have a decreasing amount of nuclear power. Until very recently, Europe was also going to almost eliminate nuclear power, though since I've made these slides, that picture has changed for the better. You may have heard the announcement that France is going to build 14 new nuclear power plants. Sweden is building advanced reactors. The United Kingdom is building advanced reactors. It's getting to be quite exciting. But the center of the nuclear world is still in Asia. In fact, when I visited Sendai, I'd like to tell you a quick story. The first day I landed in Japan, I went to Sendai. And the second day I went to Japan, we visited the Onagawa BWR nuclear power plant in order to conduct some analysis of primary water piping corrosion. So my first real day in Japan was inside a nuclear power plant, taking radioactive samples. I'm also proud to say that the Onagawa nuclear reactor has been cleared for restart. This is the reactor closest to the 2011 earthquake and tsunami. And so this shows the resilience of Tohoku EPCO and the Japanese people to continue this pledge of nuclear and green power. Despite political opposition, we need everything we can get: solar, wind, biofuel, and nuclear together to prevent climate change. And I predict that the center of world nuclear will continue to shift to Asia, making your education and careers even more important. And the question is the world doing what it must? There are now more environmentalists who agree that we need to keep nuclear plants open and build new nuclear plants in order to prevent climate change catastrophe by 2050. But this is the feeling of many of the people. In Europe, even though the governments have agreed to start building more nuclear plants, nuclear is still very unpopular, despite the fact that I believe it's what we need the most to combat climate change, and it's why I'm speaking to you today. So the question is, why is nuclear so unpopular despite the fact that it could help solve the climate change issue? And why is nuclear decreasing in the US? I'm showing you now a graph of the projected amount of nuclear power in the US as a function of time. And by the year 2049, if nothing changes, there will be no nuclear power in the United States. Right now, nuclear results in 20% of our total electricity and most of the carbon-free electricity. If this disappears and is replaced by natural gas, this will be a major disaster for climate change. So I have a theory, is that most nuclear education still follows the old models of the 1960s. When I attended nuclear physics lectures, even in the early 2000s, this is what they looked like. You've probably seen some lectures before where you just have a professor writing equations at the board, talking to the board, maybe not talking to you. And this was me. Well, I mean, I wasn't a blonde-haired girl, but close enough. This was me during a lot of my nuclear education. And we see it in our students that many students who major in nuclear power end up working in finance or starting a bakery or going crazy or something like that. So we need to change this. So our number one issue in nuclear is how to attract talented people. There are lots of smart students and smart people in the world. The question is, how do we convince them to dedicate their lives to generating carbon-free energy with nuclear power? And so I'd like to show that nuclear education at MIT is different from many other places that I've found. And part of this is to excite you to come to MIT, either as an exchange student or a graduate student or a postdoc, to study with us and see how we do things differently. For example, when we focus on learning objectives, we next talk about making nuclear personal. You might not think that nuclear is a very personal field like biology, where health and wellness affect all of us, psychology affects the way we learn and the way we perceive the world. But we show you that nuclear is a very personal field. You can discover yourself through the lens of nuclear physics, through innovative new educational initiatives and experiential or experimental learning. And I'm going to show you some of these examples today. Also, this is a common acronym in our field for post-irradiation examination. We focus now on design rather than just physics and theory, the old method. We now focus on what can you develop that's new types of reactors, new policy for regulation, new methods of combating climate change that marry nuclear and other renewable energy initiatives. We also focus on assessment, since this is an educational initiative, but also communication, because it's not just important that you learn the basics of nuclear, but that you can communicate it to the public. Because in my opinion, the reason nuclear is so unpopular is it hasn't been properly communicated to people. What are the risks and what are the benefits? And so we focus on communication very clearly. We also focus on community, because everything that we do in nuclear, it affects all of us. If we can generate more carbon-free electricity, that benefits all of us. If we have radioactive waste that somehow escapes its containment, that hurts all of us. And finally, outreach, which is why I'm outreaching to you today, to join us in this fight against climate change and for nuclear power and nuclear physics. Overall, it's moving the field from a discipline, a field of study, senmon to yokotoba, to transdisciplinary, something higher than a senmon or a specialty. And so transdisciplinary education, to explain what this means, is about issues facing society, not a field of study. So when I talk to my students nowadays, they're not necessarily interested in studying nuclear. They're interested in changing the world for the better. And so what we're starting to propose is that the subjects should not necessarily define the curriculum. I quite like this quote. There is only one subject matter for education, and that is life in all its manifestations. All of us want to study to do good, to help humanity, maybe to make money, but definitely to help humanity. And therefore, we all study the same thing, which is the study of life and how to improve it. And this is the basis of transdisciplinary education. Whereas subject-based learning, you can study subjects in isolation. For example, you can take some courses, maybe you get good grades and you get a degree and that's it. This is low on the ladder of educational quality. Whereas you can become aware of other fields without doing anything about it. But when you start integrating teaching and learning and you start sharing knowledge, correlating knowledge between things, you get to an even higher plane where we encourage our students to integrate the knowledge they have from not just nuclear, but all their other disciplines, including sociology, humanities, anthropology, like I'll show you in some of our examples. Then you start to get into the transdisciplinary, where you're focusing on the issues and how to solve them, using everything you know, not just one field of study. And so one thing I've redesigned MIT's nuclear curriculum, and one of my favorite things I like to say is we need to be more encouraging of responsible insanity. Responsible, meaning that the things that we do are safe. Insanity, meaning these are not what you would expect normal nuclear students to do. I want to give you some examples. Specifically, an experiential example in my 2201 Introduction to Nuclear Physics class. So let's say I asked you to calculate the radioactivity of a banana. This is a problem that you might find on a homework assignment. There's two approaches where you could start with this. One of them is the purely analytical. You can set up some equations, you can solve those equations, and calculate the radioactivity of a banana. But probably you will forget this by tomorrow morning, if not sooner, because this is not personal. This is not experiential. This is not community-driven. So instead, what we do in my class is I ask the students to measure the radioactivity of about 400 kilos of bananas. So I went to the grocery store and I bought about 1,000 bananas, and I asked each of my students to take 25 kilos home and peel them to remove the outside, burn them to remove the water and the sugar, and concentrate the potassium and other isotopes in the bananas, and then collect the ashes and put them in our gamma spectrometer and measure the amount of gamma radiation coming from the decay of potassium-40. This ends up with the same result as you would get from a calculation, except none of the students will ever forget this. If you see the sorts of faces people were making, this was one of the most memorable activities of their entire MIT career. That's what I'm here to do, is if I make memories, then learning can begin, because minds are opened up. And honestly, it's a lot of fun. And when things are fun, it's easier to pay attention. Then I can give you the calculations, and you can check your work using the spectrum that you measured yourself. Another example we like to do is what's called the MIT graphite pile. In neutron physics, this is typically one of the most theoretical, calculation-heavy, and boring classes in the nuclear curriculum. So we sought out to make it less boring. In the early 1950s, an undergraduate built a 2-meter cube of graphite fueled with 2 tons of metallic uranium fuel, where you could insert the fuel into the graphite, measure the reactor criticality. We've revived this graphite pile so that our students will actually put the uranium rods into this graphite pile, measure the neutron flux, and check their calculations. And I see that Eva Lesowski is on the call too, and I'm wondering, Eva, if you were part of the group that got to make this graphite pile measurement. So feel free to say in the chat if you were, I'd be excited to know. We also make things very personal. So I want to show you an example that we did this year in my nuclear physics class, including the students from Tokyo Tech who came on exchange. I asked every student on the first day of class to clip their toenails, and we put them in the MIT reactor to study the process of neutron activation analysis, or NAA. Instead of looking at nuclear reactions from a theoretical standpoint, I asked the students to discover something about themselves using their toenail clippings inserted into MIT's nuclear reactor and measure the radiation using the same gamma spectrometer. And we found some interesting trends. Without giving away any personal information, our students who grew up in China exhibited more arsenic in their toenails. It was not a dangerous level, but we could measure the higher levels, which shows you what's in the water and in the environment. And we had students from the US state of South Dakota that had 100 times more gold in their toenails than the other students. I asked this particular student, did you remove the toenail polish? And they said, yes, I did, but I grew up in South Dakota, and we have many gold mines in the state, which leads to gold particles in the water, gold incorporated into toenails, and we could measure this in the nuclear reactor. So when I asked the students to calculate the amount of arsenic, gold, chromium, and selenium in their toenails, they did so with their own data, and they learned something about themselves and about nuclear physics at the same time. And this is an example of some of the spread in environmental contaminants that we found in these students. So the scandium levels, for example, were all over the place. There was quite a tight amount of selenium because everybody needs some selenium to survive. The arsenic levels varied a fair bit. The gold varied even more. And we emphasize the process and the method of solving problems, not the answer. So I want to give you an example. This was a problem set that I'm sure Ava will remember well, where I asked you to calculate the amount of radiation you get by sleeping next to another person. So if you have a boyfriend or girlfriend or other significant other, if you spend the night together, you irradiate each other. And I asked the students to calculate, how much do you irradiate each other if you sleep like this? And I give them the answer, because the goal here is to teach the process. It's not important to me if you get exactly this answer. It's important to me that you can develop the problem on your own. So we emphasize a problem-solving approach, open-endedness, and flexibility. For students of most countries who are not in America, this is often a scary thing for them, because in school they emphasize correct answers and they emphasize getting good grades. When we bring you to MIT, we throw that all away. And I want to learn how you think. And I want to teach you not what to think, but how to think, how to solve your own problems, how to pose new problems, how to find information you need in the scientific literature, not so you can recreate the old, but so you can create the new. And that's what this curriculum is all about. So for example, I teach the students how to decompose this problem into a one-dimensional integral, where you can develop a new analytical solution based on your knowledge of nuclear physics, radiation dose, and photon interactions, where we integrate all of this information into one coherent package. Now, to show you some real-world examples of this discipline in action that bring in the personal, the experiential, and the innovative. We also ask our students to take apart things in their daily lives. Let me just get rid of the laser so I can show you this. To explore the world around them and how things actually work. So what you're looking at here are americium sources for smoke detectors that work via alpha emission. And so I had the students remove these from their sources, sprinkle some zinc sulfide scintillating powder, and you can actually observe alpha decay happening in phosphorescence from these photons. In fact, each of these pixels represents the light from 8 photons of radiation. And so yeah, Ava has a good point, is that even for a lot of students in the United States, this approach is really scary at first. It's not just for students outside America, because in US high schools, we also emphasize good grades, correct answers. And in many state schools, they emphasize good grades and correct answers. but that's how you learn the past. It's not how you invent the future. At MIT, we have an American expression I would like to teach you. Learning at MIT is like drinking out of a fire hose. In other words, you're given so much water at a time that you feel like you're going to explode, but somehow you're able to swallow it, and you come out stronger on the other side. Now I want to show you what some of our undergraduates have done in terms of innovation and design with the way that we teach them things. And so all of these projects are things that our undergraduates have done while still at MIT. And many of these projects included visiting students from Tokyo Tech. Their first day of MIT, they've never learned nuclear, they've never learned electronics. We give them a Geiger counter kit, and we ask them to assemble, test, and use this Geiger counter kit to find radiation sources in their environment. So you're looking here at a bunch of students from high school. They haven't started university yet. And if you ask them at the beginning of this, do you think you could build a Geiger counter? The answer is probably not. And within 6 hours, everybody does. And so we teach them that you can do a lot more than you think you can, even when it comes to nuclear. In our 2201 nuclear physics class, I give a prize to the student that finds the most radioactive place in the city of Boston using the Geiger counter that they built. And we found some places that are 6 times more radioactive than the normal background radiation just in the city. So I would challenge each of you to try to do this in Tokyo. And if you would like one of these Geiger counter kits, send me your mailing address and I'll send you one, along with the instructions and tools for how to build one. And so we like to say that nuclear design should not end up in a desk. It should change the world and it should matter. So in design courses, we shouldn't just develop a reactor design that will never be built. I asked my students to do something that would help humanity using radiation, and it should not be a new nuclear reactor. Among the many ideas that the students came up with, one of them was to take recycled plastic that would have been burned, irradiate it using gamma rays, and put it into cement and concrete. And the students found, using a series of compression tests and other irradiation experiments, that adding this radioactive plastic to concrete made it 15% stronger than conventional concrete, because the irradiated plastic chemically changes the nature of the concrete, resulting in lower porosity and less cracking. This was done by undergraduate students. This resulted in 2 scientific papers, 2 US patents, and a startup company, Micon Technologies, that continues to this day. So even more impressive, in fall 2020, when everybody else was hiding at home due to coronavirus, the students in our 22033 course designed an anthropologically informed, culturally acceptable way to decarbonize the city of Ulaanbaatar in Mongolia. And I note that we have a few Mongolian students on the call today. You should know that we're continuing this work to this day. This started off as a conversation between one of my colleagues that I met at Tokyo Tech, Professor Munkbat Byambajov, an early student of Professor Obata, and I. So back during a conference at Tokyo Tech, Munkbat was telling me about the pollution problems in Ulaanbaatar and asked whether we could use our nuclear knowledge at MIT to help remove the pollution and decarbonize the city. So once I became a professor, I set our students to work building a scale model GER to decarbonize Ulaanbaatar, the world's coldest and most polluted capital city. So my apologies to the Mongolian students who already know this story, but to the rest of you, I want to show you what our nuclear students, together with Tokyo Tech students, are able to accomplish after an undergraduate nuclear education at MIT. So Ulaanbaatar's most vulnerable residents live in gers, or nomadic felt tents, and they are largely dependent on the government for livelihood. This is what Ulaanbaatar looks like in the summer, looks quite nice. And this is the winter. So the climate change problem is especially severe in Ulaanbaatar because it's surrounded by mountains. It burns coal in order to stay warm because it can reach minus 50 degrees Celsius in the winter, and the residents have no choice but to burn either the coal or charcoal briquettes in these traditional stoves, one of which we bought and had shipped over from Mongolia in the 2020 pandemic. The stove is both the literal and symbolic heart of the household. It heats the house, it's where cooking happens, and it's the center of family life. Unfortunately, the government required residents to stop burning coal and use these charcoal briquettes, which produced carbon monoxide if burned incorrectly. There's an expression in America, is never barbecue indoors. Well, that translates here, where people's children have been dying because of carbon monoxide inhalation. This year, because the border with China is closed, the residents did not have enough material to make these briquettes, and they have resumed burning coal because there's no other economic alternative. And so I asked our students to figure out a way to break this dependency, not just eliminate the pollution and the carbon monoxide and dioxide emissions, but also to help free the people from dependence on the government for their livelihood and daily heating. There are some solutions proposed by other groups, for example, adding insulation to the gears and adding electric heaters, which the government has been giving out. There's some problems with this, though. This solution from another university cost about $400, and the median annual income is only $1,100 per year. This is far, far too expensive. I also have a question for all of you on the call that I'd like you to put in the chat. If we use electric heaters in the gears instead of burning coal, this makes the pollution 3 times worse. Can any of you please explain why? Why does switching to electric heating make the pollution problem 3 times worse? I'll wait a few seconds for anyone to answer in the chat. Yeah, Ava's got it. It's less efficiency and relying on coal plants elsewhere. Thank you. If you use an electric heater, the electrons have to come from somewhere. Right now, they come from coal. So by removing 1 watt of coal from a gear, you must burn 3 watts of coal in a thermal power plant to produce that electricity. So while it looks like you're removing the pollution from people's homes, what you're actually doing is just moving it outside the city. But as we know, pollution and carbon monoxide float about in the air. It doesn't help, it actually makes things worse. So our students calculated that if we were to insulate the floors and the wall of the gear by a factor of 4, we would be able to reduce the heating needs such that we could use molten fluoride salt, the same coolant as proposed for a nuclear reactor and concentrated solar power, for all of the energy needs, both heating and cooking, for an average family living in a gear. So our students worked on making affordable insulation and a molten salt heat brick in order to remove the coal completely from the equation. So our students built a 1/6 model gear, a felt tent with the same thermal resistance as you would find in a real gear. They built different types of insulation using locally available materials like rock wool and plastic bottles. They inserted a traditional Mongolian stove into here and devised a molten salt energy brick that would go in here, measure the temperature as a function of time to confirm the gear can stay warm enough through the night, and actually heated this up to 400 degrees Celsius and showed that they were able to power the gear with 0 emissions. The last part of this adventure to be solved is in how do you provide the heat to the salt bricks themselves. At the beginning, we think this will be done with concentrated solar power, because Mongolia is a very sunny place, and the less pollution there is, the more sun there'll be, and the easier it will be to harvest solar, and eventually to switch to nuclear power, to small modular reactors. where the government in Mongolia is becoming much more interested in nuclear power because of this energy crisis. And so there's a way that you, as undergraduates, can help decarbonize 1 million people in the next few years. That's our hope. By partnering with the National University of Mongolia and the Mongolian government, we hope to deploy the system in just a few years, not decades, not tens of years. In a few years, we want this in people's gears. And so we were able to devise this solution, which would cost a family only $20 to $60. There would be a payback period of 8 to 10 months. And that means that families can afford it. That means that the government can continue making money off these salt bricks instead of just the coal. It means that we can shift the coal mining industry to a salt brick building industry, and that nobody in the solution should lose out on their livelihood. This is what I meant by integrative. It's more than just a technical solution. We teach our students to consider the people involved in everything they do. It's not just enough to insulate a gear and add an electric heater and assume that your solution is complete. You have to consider the economic resources of the people, the payback times allowable by the government, the current political climate, which changes every day, in order to have an engineering solution that people will accept. And so we're starting a new field which we call anthro-engineering, or anthropology engineering, in solving engineering problems with people first, not with technical challenges first. An example of this is another project that came out of our design courses, the arc reactor, which spawned Commonwealth Fusion Systems, a new startup company that just raised almost $2 billion to build a fusion power plant within 15 years. There's a lot more science that has to be done, but this all started from an integrative, people-first MIT student design project. They didn't ask, how can we contribute to ITER, this gigantic fusion reactor that's too big to build? They said, how small does a fusion reactor have to be for a utility electric company to buy it? And they started there. And already they've raised more money than all the other fusion startups combined, because their design thought about people first. And a lot of the success in this regard is creating engineering communicators. So within our department, we have a communication lab specifically geared towards teaching engineers how to communicate with each other, how to communicate with the general public, how to be discipline specific, but still create this active learning supportive environment, and undergo data-driven assessment to make sure that our methods are actually working. We do this by hosting one-to-one peer coaching sessions. Instead of teaching engineers to write using writing experts, we teach engineers to write using communications experts in their department. And this allows students to learn how to communicate with other engineers and make sure that they're understood, with the general public. And the ultimate test is if you can explain your research to your grandparents, then you know you've done it very well. We hold workshops, we have partnerships and other online resources in order to turn our students into expert scientists and expert communicators. Because without both of these skills, you cannot have any impact. Of course, you need to know the science and engineering to solve problems, but you also know how to communicate to humans. Because if you can't communicate your ideas, then how will people know? So we emphasize communication equally important as technical specificity. And beyond MIT, the last thing I want to encourage all of you to do, which is something personal, to join our community and as part of my outreach, is to encourage you to come to MIT. And I want you to meet some of the faces of the students who came with us just last semester. This is Kageyu and Kenta Kubota, who joined us for this fall semester and took our nuclear design courses, our nuclear physics courses, research in our labs, and generally had a fantastic time at MIT. So when I've talked to students throughout Japan, there's this impression that MIT is this amazing place. That's true, where everyone has to be super smart in order to get in. That's true. But the difference is it's not too smart for anyone. I would encourage you to say, if you've been admitted to Tokyo Tech, you can come to MIT on exchange. You have the intelligence and you have the skills that you need to come join us, like Kage, like Kenta, to do good in our classes, to achieve things in our research labs, and to build ties between United States and Japanese students so that we can continue to work together, have happy memories of working with each other, and work together more closely to build a nuclear future together. And I know I'm putting Ava on the spot, but Ava is a perfect example who came to Tokyo Tech on an exchange program. And now she's back in Japan pursuing a master's degree. And it's these sorts of experiences and people that we want to create. So this could be you coming to MIT. And that's where I'd like to stop. I know it's not been 1 hour yet, but I like to give lots of time for you to ask any questions that you'd like. そして日本語でも英語でも質問してください。そして一生懸命日本語で答えるようにしますが、まず英語で答えて必要が何ですか? So, if you have any questions for me on anything that you've heard today, from our philosophy of nuclear education to how you can come join us at MIT, please let me know in the chat or unmute, and I'd love to hear your questions now.
Okay, thank you, Professor Schultz. There's a question and the comment time, and is there anyone to ask it? Well, maybe
it takes a little bit of time for people
to that's right. Yeah.
think of their question. I know it might be difficult in English. Yeah, Alexandru, please.
Oh,
yeah. Oh, hello. Can you hear me?
Yep.
Oh, perfect. I wanted to ask, how much time do you dedicate, to this more practical approach to learning and balance it with the actual theoretical study?
Sure, good question. So we make sure that there's a hands-on practical course in every single semester. Some of that we've done by creating new courses like these design courses. Some of it we've done by adding laboratory exercises and discoveries to existing courses like nuclear physics or neutronics or radiation detection and measurement, so that every semester you'll be actively learning. Now, there's still a lot of theory and a lot of difficult problems to solve, but we know that people learn in different ways. Some people learn best by being spoken to in a lecture. Some people learn best by reading. People like me learn best by experiencing. And so I wanted to make sure that everybody has the method of instruction they need to succeed. So did this answer your question?
Yes, thank you very much. I wanted also to ask, when do these innovative ideas come? Usually in the class, they come after the class, they come while actually doing one of these experiments, and usually I'm like, oh, I have another idea, let's try it.
Yeah, great question. So I'm very delighted to say that many of these innovative ideas come during the class. It's when you're immersed in not just the class, but in the community of other students with fresh ideas. I was talking recently to the CEO of X Energy, Dr. Eben Mulder. He was telling us how he had devised a lot of new ideas for reactors and other things. And he said, the only reason I was able to do so is because nobody told me it was impossible. So he solved a lot of new problems that everyone said was impossible by being in a good group of people that nobody knew that people think this problem is impossible. That's the environment we create in these design courses. We, the professors, don't tell you what to do. We tell you how to do. And the students have often come and surprised us by what they come up with simply because they're taking a fresh look. They think differently than us. They've got experiences that, my mind, I'm 38 now. Compared to these students, my mind is made of stone and fossilized. So it's amazing what new people can come up with old theory and some freedom to innovate.
Thank you very much for the answer.
Sure. So does anybody else have any questions they'd like to ask?
I guess I have a question.
Sure. Yeah, go ahead, Eva.
I was trying to start my video, just okay.
Mhm.
Yeah, you were talking like about the fusion, the new fusion research and like different energy sources, for different problems that you mentioned, that were started in that design class. But as for like fission reactors, because maybe many people here are working on fission reactors also, there are many technologies, but in your opinion, or I don't know, what can you like, do you have like a fission technology that's looking hopeful to you, or in your opinion, like what is the most the best? I don't know, I don't want to say the best one because like all have their own merits, but what is your opinion on the outlook of different fission technologies that are coming up?
Yeah, good question, Ava. And in my view, there are 3 fission technologies that all look to be very near-term deployable and practical. And the proof of this is that there are 3 technologies which are being built in the US now, and within 5 years we expect to turn on. This is high-temperature gas reactors, like the X-Energy XE100 reactor, where there's already a site picked out in Washington and the public has accepted to build a nuclear plant there. There's the TerraPower Natrium reactor using the liquid sodium. And there is also the Kairos molten salt reactor using high temperature molten fluoride salts. The benefit of each of these 3 designs is that they cannot melt down like a water reactor can. There's nothing to make hydrogen, so there's no chance of an accident like Fukushima. They're very passively safe. They're on the small side, and lower power density helps mitigate many types of accidents. And they're economical. That's the most important thing. That in the end, when you talk to certain people about why they won't build nuclear plants, and if you can convince them, we can deal with the waste, we can deal with the proliferation, we can deal with the physics, they always say, but it's so expensive. Luckily, these 3 technologies are not so expensive so far. They're in the $1 billion range for a few 100-megawatt reactor, which is 10 times cheaper than your average light water reactor today. Light water reactor technology appears to be too expensive when it's large scale. There are also some small modular light water reactors like the NuScale and GE units being built in Oregon and up in Darlington in Canada. So I would say at this point, we need an all-in approach. We need to start building and gaining experience with these new fission designs, because we can decide all we want on paper or in the laboratory, but until we build a test reactor, we don't really know for sure. So I'd say those 5 are the most promising ones I've seen. So does that answer your question, Ava?
Yeah. Yeah, because I'm just starting to get into my research topic. So I'm trying to decide, what should I focus my energy on, or what might I be interested in. So thanks for your advice.
You bring up a good topic too, is that many people talk about which design is the best. And I think the word best is inapplicable when it comes to different designs. The people are most important. If you can convince a group of people to fund it, and you can convince another group of people to build it, and you can convince another group of people to allow it to be built in their territory, then you've got a winning design.
Okay.
Yeah, Alexander.
Is it possible to ask another question?
Yeah, keep going. We got plenty of time.
Talking about the new types of molten salt reactors, the 3 types that you mentioned, like from your experience, at least I had the opportunity to work with the regulators back home, and I know that is the biggest hurdle usually, getting the design licensed as being safe and being run. And realistically, how much time do you think there would be necessary for those in the US, for the NIC to give the go for it? Because it's easy to guess backup. It's easy to make a first-type power plant, like testing one, but actually making it commercially viable and licensed, that it's safe. That's gonna be the biggest hurdle usually.
Yeah, so that's a great question, is how long and how hard is it to actually get a new plant licensed? Luckily, the US Nuclear Regulatory Commission has realized that they need to get much more efficient. And there's a whole new wave of people that have joined the NRC, including many of our students. And so I believe it's going to take no more than 5 years for some of these smaller designs to be licensed and ready to build. There's a few things that are going for it. The Congress has required that the NRC make a licensing pathway for advanced reactors. There's also a guarantee that they'll at least respond to a pre-licensing application within a short time frame, like a year or two. And they've already begun responding to some of these pre-applications. And finally, the fact that a reactor is smaller, like I said, things that are smaller and lower power density, the accident scenarios are less severe. And so it naturally follows that the number of real difficult technical questions that the NRC will pose will be smaller. Now, I should mention too that just because someone proposes a new reactor does not mean the NRC will accept it. And I want to give an example of the Oklo reactor. So some of you may have heard of Oklo. They're another startup from MIT students proposing to build very small 1 megawatt nuclear reactors. They applied for an NRC license and they were rejected, completely flat out rejected. And the reason the NRC gave was that they refused to do accident analysis and assumed that because their reactor is too small, that they won't have any major accident scenarios. This is false. And so this is to me, some people view this as, oh, the NRC is not licensing advanced nuclear. This is a good thing to me because it means that the NRC is moving fast and it will only accept high quality. We don't want any sort of low quality nuclear design that hasn't been vetted to get through. But at the same time, the answer from the NRC came very quickly. And so that gives me some confidence that this 5-year timeline really will be followed because they've been able to do so in less than a year for some of the pre-licensing applications. So does that answer your question, Alexander?
Perfectly. Actually, it's very hopeful news. 5 years sounds really hopeful. I really hope they keep up the work for it.
Me too. I'd say the data looks good, that the NRC is doing pre-licensing applications in the 1-year time frame. And the fact that many of the new designs are smaller, they're both responding to market desires. If you ask a nuclear utility, they don't want to buy a 3,000 megawatt thermal power plant and have their money stuck in a loan for 30 years. They want to go smaller. And that also helps the licensing process because there's less power in the core and the theoretical worst accident is less severe.
And the whole investment is also less low and the whole deal, because usually a power plant deal is usually a 100-year deal of actually licensing it, building it, exploiting it, then actually commissioning it.
Yeah, some of these reactors don't see payback for 20 or 30 years. It would be nicer if it was 3 or 4.
More attractive. Thank you very much for your answer.
Yeah, my pleasure. So does anybody else have any questions for me on the way we do nuclear education at MIT, or how you could try to join us, either in research or in a semester exchange?
Okay, can I ask some questions?
Yeah,
yes.
Professor Katabuchi, please.
Okay, yeah. Yeah, you showed a very interesting example for education, like bananas and radiator nails in reactor.
Mm-hmm.
And actually, how do you find a good actually problem for students? Yeah. How do you get the idea? Actually,
that's a good question. So for every problem set, I start with the learning objective. So what do I want the students to know? I'll give you another example. Let me see if I can pull this up in real time from my server. Mm-hmm. Let's see. Sorry, just give me 1 second to pull up another example that I think will illustrate this point well. Found it. Okay. So I wanted to talk with our students about medical imaging and what sort of X-ray intensity is used to generate image contrast.
You're sharing some slide now?
I will in just a minute. Yeah, not yet.
Okay. Right.
So I wanted to teach my students how X-rays are used in medicine in order to image bone or muscle or things. And so instead of here we go. Instead of having the students just make some calculations to say, okay, you have a person with this much height and this much weight or whatever, I sent each of the students over to get a dual energy X-ray scan or DEXA scan, where I actually said, well, rather than use historical data or calculations, I had each of the students sit down on an X-ray table and measure their own mass density. And they can tell from this graph, where's the muscle, where's the bone, where's the fat. And then I had them look at the photon attenuation spectra for these three tissues. And I asked them to say what X-ray energy was used in the creation of this. But at the same time, they get to learn something about themselves, like their percent fat in different regions, maybe the lean mass, the fat mass. So they get to learn a lot about their own personal health, in addition to using their own data in order to learn nuclear physics. So for every problem, I would first write the problem in the old-fashioned way, where you say, calculate the X-rays intensity required to make this image on that person, and then ask, how can they do it themselves? So instead of calculating natural background, I have them measure it with a Geiger counter. Instead of making medical X-ray calculations, I go give them an X-ray. Instead of teaching them about reactor kinetics, where you change the power level, we put them in front of the MIT reactor and they raise and lower the control rods, and they control 6 megawatts of power with one little dial. So for every problem set, I ask, how could they physically do this and generate their own data? Then the most important part is I remove half the problems, because it takes twice as long to do one of these experiential problems as it does to do a theoretical problem. But every year, for example, because now the banana lab is getting old, it's kind of boring, the students vote on which food they would like to measure the radioactivity. And we found that tomatoes are much more radioactive than bananas due to higher potassium content. Or I try and include things from my own personal experience. I'll show you something fun that we did just this year. I wanted to get out of America because COVID was driving me crazy. So I went to Iceland and I hiked this volcano. So I was at a new volcano. This is a video that I shot, by the way. So I was at this volcano. We were about 500 meters from the eruption. And I had read somewhere that the radioactivity in the center of the Earth is much higher than the radioactivity in the Earth's crust. And so this volcano was a particularly deep magma penetration going deep into the Earth's core. So I filled my backpack with this lava that had just cooled a few days ago. And I brought it back to MIT and had the students measure its radioactivity and try and figure out from how deep in the Earth did this lava come. And so that way they make a measurement, they do a calculation, and they have to look up something in a scientific paper to answer the question. I want every problem for the students to do these three things. So does that answer your question, Professor Katabuchi?
Yeah, very interesting actually. I think your way is really always based on experience and experiment data, I think. Yeah, I think that's a good way to learn, I think. Some students sometimes problem to link theoretical things to real things, I think. Yeah, I see. Thank you very much.
It can be difficult to link the theory of nuclear physics to personal experience. So every problem I make personal. Yeah.
I see. Actually, you show the gigantic blackboard introduction.
Yeah.
Actually, that was how does that work? Actually, professor climb up the board and write down the equation.
Yeah. So at MIT, we have these blackboards that you can raise and lower using a stepper motor. So you really can fill this blackboard like that. It's it's impressive, and at the same time, these classes can be really boring.
Okay. Is there any other questions? I think Japanese questions are also okay, right?
じゃあどうぞ日本語で説明してください。
日本語でもいいそうですから、どなたか別に質問ありますか、他に。Well, we still have time, I think.
Yeah, we have maybe 5 minutes, yeah?
Yeah, that's right. Yeah. 簡単な質問でもいいですよ。なんていうのかな。素朴な質問でもいいので、日本人の学生さんでも。うん。ぜひこの機会に、疑問に思ったことを聞いてみてください。
ボストンの生活でもいいですよ。
そうそうそうそうそう。But after experiencing actually those things, students learn those equations, right?
Yes, in fact, as a controlled experiment, I've given the same examinations to people. I don't give out the answers to the final examinations, but the grades of the students have been improving. In fact, the grades during COVID were among the highest that I have experienced in the 7 years that I've been teaching this class. Because even during COVID times, I sent my students Geiger counters. I had them mail me their toenail clippings, and we still put them in the reactor. And I still had them go out and look for radiation in their home environment. And I still allowed them to go to local X-ray scanning centers. So even during COVID shutdown, our students participated in this active learning, and they did very well. I did not make the class easier. I did not make the class slower, even though MIT Central Administration said, oh, we suggest no examinations, maybe don't teach everything. I said, no. We're doing everything as long as the students are enjoying it. And we taught the full nuclear physics course with the hands-on components during Corona pandemic.
I see. You showed the Geiger counter, and I feel the circuit used some internal circuit, right? I see. Maybe the circuit a little bit difficult to understand, maybe. Does the student understand those? I think the principle of Geiger counter is not so hard, but maybe circuit theory a little bit difficult.
That's true. So we do give a very detailed manual on how the circuit works, because we assume students have no experience with electronics. So we break it into different blocks. We say this part provides the high voltage for Geiger counter. This part provides the speaker noise, and this way, you don't have to understand everything. But when there's interest from the student to understand what's going on, it's easier to learn this new information.
Okay, I see. They learn basic idea and components like amplifiers, and high voltage supply, and the speaker.
Yes.
Right?
So we don't just give information. We open a knowledge gap. So rather than say, here is some new information, we always ask the question, so why do you think this happened? And when there's an interest to answer the question, it's much more easy to remember than just giving information.
Nice. Okay, are there any other questions or comments?
Yeah, Alexandru, please.
Me again. You said also that we can participate or join at MIT at the lab as an exchange.
Yeah. Oh, yeah. So would you like me to explain how?
Yeah, in short, if the time permits.
Sure. So every fall, we select 2 students from MIT to come to Tokyo Tech and 2 students from Tokyo Tech to come to MIT. It's not always exactly 2. So if one year there's 1 student and one year there's 3 students, that's okay, as long as it's average of 2. And it's pretty simple. Is you take classes at the visiting institution. They count for credit at your home institution. You can also work in a research group in a undergraduate research project. And the only thing that we send across the ocean is people. So MIT pays for everything while you're at MIT. Tokyo Tech pays for everything while our students are at Tokyo Tech. And most important for Tokyo Tech students is you only pay Tokyo Tech tuition, because MIT tuition is about $60,000 US per year. You don't have to pay that. So you pay your home institution tuition and you get credit at your home institution.
Okay, thank you very much.
Sure. And the cost to the student should be, the additional cost to the student should be zero.
Thank you.
Okay, any other questions?小原先生の方から何かありました？
いや、特にはないです。ありがとうございます。
Okay, I think it's getting time, I think. Yeah.
そろそろ時間です。
Yes, that's right. I think it's gonna be time, I think. Well, we have time, but okay. If we, there's any other questions, I think we want to move to the next speaker, I think. Okay, thank you very much, Professor Short. Okay.
Yeah. Thanks, Professor Katabushi, Professor Obata, everyone for having me. It's been a pleasure to speak to you.